Okay, so one question was, which is actually going to come up today, the question which nobody heard but me, was had to do with, last class we were talking about these binomial tree models. And in the course of the calculations that we were doing, we sort of assumed that the interest rates were constant, okay? That somehow, well, what did we do last time? We did the binomial tree model for option pricing. We built this, in fact, actually it's not harmful to have it on the board again, it turns out. We built this sort of binomial tree structure to model the possible paths that a stock price can take. Okay? Actually, I have it in such a terrible job drawing. Let's leave it at this. Okay, and what the possible paths are that you could go through. And in order to price what the probability of going up or down, that was based as a function of interest rates. Okay? And the question here is, do we need to leave interest rates constant? Okay? Or not? Okay? That's basically what your question is. Okay? And now, of course, interest rates in the world are not constant. The question is, can you model them better than, or predict them better than sort of a constant? That's up to you. In one sense, the answer to your question is, this is a binomial tree and you can do whatever you want with it. Okay, that's what makes binomial trees a good thing. Okay, you're doing the calculation. Each node here is an instant in time. If you know something about what the probability, what the interest rate should be, you can put a different interest rate here at this unit in time than you can in that unit in time. Perhaps you could even, if you know that this means that the stock market has crashed, maybe you might even conceivably put a lower interest rate here than if it was high, if you felt that you had the modeling and understood that well enough. So the great thing in my mind about binomial trees is that you can put whatever modeling of the world you do into that framework. That's what, to me, makes it a very... There are a couple things that make it very good and powerful. We'll show you another way to price, okay, options today. That is, in some sense, quote-unquote, better by some ways. But one of the ways in which binomial trees are better than the Blackscholes equation is that this model assumes either constant interest rates or a very simple model of changing interest rates. With this kind of model, you can do whatever kind of local tweaking you want, okay, and still get an answer to reflect, you know, because everything is a function of local conditions, okay? If you have a vision of the conditions as not being uniform, you can go ahead and deal with that. Any questions? Okay, any questions from last time about binomial trees or options pricing or risk neutral valuation? Any of those things that we talked about from last time? Okay. What I'd like to talk about today is the sort of somehow famous Blackscholes equation. Okay, so there's, you know, so I am quite happy modeling pricing options using this binomial tree method. It's something I computationally understand. As we just discussed, I can tweak things and do things. But there is a sort of another option pricing model that's very important, which, as we will see, in some sense is conceptually identical to what we've been talking about so far. Okay, the Blackscholes-Merton model, okay, which leads to the Blackscholes equation. You can add Merton's name or not, depending upon how you feel like it. Is basically a binomial tree model where the steps are infinitesimally small. Infinitesimally small means we're talking about things that are continuous. That gets us into this calculus world. Remember, you remember math. At one point, there was calculus. In calculus, everything was continuous, and you had infinitesimals. And then you became a computer scientist, and you forgot about calculus. You didn't have integrals anymore. You had summations. Okay? The Blackscholes model, okay, is a pricing model for options that that is based on the following. It's basically a binomial tree model analyzed with an infinitesimally small time step. Okay? which is parameterized by the following things, okay? And again, we've talked about these factors before, some of which we have factored into our binomial tree model, some of which we haven't. The options prices are a function of the current price of the stock. Well, certainly that was the starting point of our binomial tree, so that we factored in. There was the dividend yield of the stock, okay? We noticed that we had prices in general drop when dividends are released. But we said that in principle we could factor that into our binomial tree model by simply modeling different jumps on the day the dividends are supposed to come out. Okay? But we agree that affects it. K, the strike price of the option. Okay? That is clearly an important thing for pricing, and it's something we kept in mind. R was the risk-free rate. Okay? And again, here we're going to assume it is constant over the life of the option. Okay? T, the remaining time until the contract expires. That was this in the binomial tree. And the one thing parameter that we didn't have in our binomial tree model so far that we discussed was this thing called sigma, which was the volatility of the stock price. Okay? The last couple of days have been interesting in the stock market, right? We go from Thursday, I guess it went down by a huge amount, then up by a huge amount, then down by a little amount, and then down by a huge amount, right? So what this is reflecting is volatility, okay? And as we talked about at one point earlier in the semester, the more volatile the stock is, the more likely it is to jump up to a high level or collapse to a low level, okay? And so that should be a factor of our model. It wasn't a factor of the model so far. We didn't talk really about it. We talked about binomial trees. We never talked about the standard sigma. Although I will assure you we could factor that in and will factor that in today. Any questions? So, in one sense, if you want to say, what is the Blackscholes formula? Okay? For the practical purposes of what you have to do for the assignment, you guys have an options pricing assignment. I said you have to implement the Blackscholes method. There is somehow, what it amounts to is under this model, with the continuous model, there has been an analysis and produced a closed form formula of what the values of the call and put options should be as a function of these 6 parameters. Okay? So if we take a look at this thing, again, they look kind of ghastly. But if we look at it, the price of a call is, according to this, described as the initial value of the stock price, S, times something, okay, where that something is a function of the dividend yield. If there were no dividends, then if the dividend rate was 0, then e to the 0 times t would be 1. Okay? So it's the initial price times some, what I'll call messy constant. N sub d is going to be the cumulative normal distribution applied to a particular constant d1, minus the strike price k, discounted, e to the rt is something about discounting it or growing it according to the interest rate. Okay? Times, again, another constant, which is derived by the value of a cumulative normal function on D2. Where D2 is this complicated looking or ugly looking function of basically all the parameters, most notably sigma, okay, sigma squared over there, which is the volatility. So one way to look at this, is saying this is a ghastly thing and I don't want to look at it. Okay? If you want to make at least a gross interpretation of it, notice that the units are right. That's the first level of formula understanding I always do. What is the units associated with a call option? What should the unit be? Should be priced in dollars, right? Okay? And if you look at it, the strike price and the starting price are both dollar quantities. So it's the difference of $2 quantities multiplied by constants. Any questions? Okay? And essentially, the terms are not completely reversed, but if you look at it, it's an analogous formula, okay, for the put option, where the strike price is now the leading term instead of the second term. Any questions about that? On one level, this is all you need to know about the Blackscholes formula. Okay? This is now an equation you can punch into your calculator. Okay? You've got 6 parameters. There are 6, there are variables in here. Okay? You have to understand what the functions involved are. But again, we know that e to the RT minus RT or e to the RT is somehow the exponent, the natural exponent, okay, value of RT. It's the discount factor of the interest rate over time, that kind of thing. The natural log of S over K. What is S over K? If S equals K, what is the natural log? What is the log? S over K is, if S is equal to K, then S over K is 1. What's the log of 1? 0. Okay, so it has no impact at that point. Otherwise, it is positive or negative. This is going to be some parameter that's somehow going to denote whether we are in the money at the current price or not. N1 and N2 are numerical functions, okay? And it's a standard numerical function. If we take a look at the normal distribution, again, here is a normal distribution, okay? What we want here is, the normal distribution is centered around 0. Basically, is going to tell you, as a function of how many standard deviations, this is a probability, right? And it's a question of how, it's a function in some sense of how many standard deviations above or below you are from, how many standard deviations above or below the mean you are. Okay? The normal distribution would tell you what that probability value is. The cumulative normal distribution will tell you what is the area to the left of that point. So if this is D1, okay, this big function n of D1 is going to tell you something about how much mass of the probability distribution there is that lies to the left of it. Is that clear? That should be, I think, pretty clear. Okay? And for our purposes, the important thing is to know that this can be computed. How can this be computed? Well, in the olden days, you would look it up in the back of you would get your Abramovitz and Stiglitz, okay, your tables of mathematical, mathematical tabulations, and you could look this thing up, okay? Now it is probably more convenient to go into Excel. There is an Excel function that would compute this thing. If you're not in Excel, there is a polynomial approximation to what the cumulative normal function is. And that in some sense, by implementing that, okay, you can compute this thing without too much effort. Any questions? Okay? Presumably, even before you implement that, there are scientific math libraries for whatever programming language you use. And almost certainly that formula exists there. Any questions? Okay? So the good news is that all of these things are commonplace with the, certainly even my favorite programming language has this and this. Okay? Something like this shouldn't be too hard to find. Any questions? So here is an example, just to sort of, since you have to do this on your programming assignment. Let's just go through and take an example of this, okay? Here again are a set of parameters, okay, for what you need for this thing, okay? The strike price and the starting price are both in dollars. Those are easily looked up. What? Well, right now these are just parameters, okay? If you want to price call or put, you have to plug it into the right equation. But both of them are still functions of the same underlying values. Okay? Any questions? There's a dividend rate. Okay, you'd have to look that up for your stock. There's a time period. In the way this formula is written, the time is given in years. So if you want to price it for a certain number of months, 3 months is a quarter of a year. Okay? The interest rates are given for a year, as is the dividend rate. More importantly, the volatility, the stock volatility, is given in terms of annual volatility. And we haven't talked that much about volatility. We will in the next section of the course more. But I find annual volatility a little difficult to think about. Okay, so why don't I say this thing? What do I mean by volatility? If you want to compute what the volatility is. Somehow the volatility is associated with the standard deviation of the... They want the sigma to be the volatility to be the standard deviation of a continuously compounded rate of return in a year, in 1 year. That I have a difficult time to understand. Okay? But I can understand the following things. Okay? If you have an annual rate of standard deviation of sigma, the standard deviation over a time delta t is basically sigma times the square root of delta t. And let me try to explain this again just to understand this. Do you remember the coin tossing example? Okay? If you toss a coin, a coin 1,000,000 times, how far from the mean in terms of the difference from heads to tails should you be after you've tossed the coin? Let's say you toss it n times, right? Does anyone know roughly what the deviation here is? You toss a coin n times. How many times? What's the expected difference between? What would be expected deviation between the absolute value of the difference between heads and tails? It's something times square root. Okay, that's the way I think about it. Okay. So what's interesting about it, if we picture the volatility as being this thing at the end of a year, okay, the deviation here is going to grow somehow as a square root of the amount of time that you do. Does everybody see that? The amount of difference, let's say, between heads and tails, the difference between that is going to, the deviation is going to be somehow basically around square root n. If you played this game for 1 day, how much difference is there going to be between heads and tails? 1. Okay, so for 1, there's a big deviation relative to the number of days you've done. As n increases, the deviation grows as the square root of n. Okay? And so, as for a similar kind of reason is why the square root of time thing shows up in this equation. That's my way of thinking about it. Okay? So if you want to go from annual volatility to daily volatility, okay, you need to adjust it by this factor of the square root of the amount of time that you're doing. Okay? Any questions? To measure the daily volatility, well, that is the volatility of the returns is somehow how much does it go up or down on a percentage basis each day. Okay? Certainly you could take a look at the stock table, okay, and figure out every day what was, over the last 100 days, what was the percentage increase or decrease. Okay? Given that, you can compute the standard deviation of these numbers. Okay? That would give you the daily volatility. By using this expression that the standard deviation over time, delta t, is sigma times the square root of delta t, that gives us a way to move back and forth between a daily volatility and an annual volatility. Okay? Does that make sense on some cosmic level? Again, concretely, when you looked at that example, they had a 25% annual volatility. That maps to, if I did my calculation right, a 1.57% daily volatility, which is quite reasonable in more peaceful times than we live in today. Any questions? Okay? So there is a notion of an annual volatility, and this gives you a basic way to calculate it. Any questions? One issue when you go and calculate it is there's a question of how many days are there in the year. Okay? If you're now going to try to convert daily volatility to an annual volatility, how many days are in a year? Okay? I was taught it was 365. But if you think about it, in a stock market, there are not that many trading days. If you broke the world down into there's trading days when things move and you measure things, and non-trading days, we only care about the trading days. Okay? And so that's why in this case we basically took the annual rate and discounted it by the square root of 1 over 252. Any questions? Okay? So what is interesting now? We now have, I claim, a way to get all of those parameters. Okay? These you can all look up in the newspaper when you figure out what the option is. Not in the newspaper, but in the whatever the specs of the option are that you're buying. And this, in principle, the volatility, we just showed how you can calculate. Okay? In some sense, by observing volatility in recent times. And we'll have more to say on that in a couple classes. Any questions? Once you have those parameters, then you just basically punch it into the formula. Okay? And I don't really expect you to read it, but I expect you to believe me that now that you've got the formulas with the right time frame, you can compute what D1 is. You can take D1 minus sigma delta T to compute what D2 is. You can look up the normal values, use some library function to do that. If your library function is addled enough that it doesn't like negative numbers, note that if you only have a cumulative normal function that works on positive numbers, note that if you take a look at what the value is for minus D, this is a cumulative probability distribution. Okay? That means the area under this distribution has to have a total value of 1. Right? The normal function is perfectly symmetric. So the area to the right of D1 is the same as the area that is to the left of minus D1. Okay? And so once you believe that, okay, the value of minus D1 is the same as 1 minus the value for D1. Any questions? So bottom line, using all this, I claim you guys can compute this thing. Any questions about it? Okay? And again, once you've got those parameters, N1 and N2, D1 and D2, you basically can go and just plug everything else in. And eventually it will come up with a magic number for what the price of the option is. Any questions about that?
This number is
This is going to price American options, yes. Yes. Any questions? Okay, and as I described, that's just the calculation for volatility. Okay? Any questions about that? So what is good about this? Okay? In one sense, if we go back to your homework assignment, what is your homework assignment in here going to be? Okay? You're going to be pricing options, right? And I ask you to do it 2 different ways. I ask you to do it by binomial trees, and I ask you to do it by Blackscholes Formula, right? Now, one of the good things about the Blackscholes, what makes the Blackscholes Formula important? One is that it is a nice, easy way to calculate it. It is in principle something that you plug into a calculator, okay? That means that it is easier to compute. That means it is faster to compute than going through this big, complicated numerical method, okay? If you are a hedge fund looking desperately for what options are mispriced, Okay? So you can take advantage and buy them before somebody else does. You are interested in the speed of the computational method, right? Interested in a lot of things, but among other things is the speed of the computational method. And so if you believe that the Black-Scholes equation does the right thing, it is a good thing because it's a faster way, an easier way to compute it. It also gives us a model to understand what the individual factors are on price and how they affect what the price is. Okay? And that is interesting to think about. And so on a level of understanding what's going on, having a closed form is a good thing. Any questions? All of that should be believed. What I'd like to do now is to go through some of the parameters, okay, that we have for pricing options and see what effect they have on the options prices. So let's say now that we know actually really how to compute these things, you could take a set of options parameters, all but one of them, and then plug it into the formula with different values and graph it and see what happens. Okay? So let's look at what the impact of certain important parameters are on the options price. Here is a question of what the current impact of the current price of the option is. We're assuming there's a strike price here of 100. Okay? As the current price of the option, as the current stock price goes up, okay, then what do we see? That of course the call option goes up, the put option goes down. That obviously makes sense. Okay? It looks like put and call prices are approximately equal. Okay, right around when the current price for doing when you're buying the option is at the strike price. Does that make sense? Let's think about this. Should the put and the call price, okay, be equal when the strike price is the same as the current price? Let's think about that. Does that make sense? Okay? In principle, it seems like it should sort of be true around there, because there's no more likelihood for the price to go up, we're assuming, than the price to go down. Okay? We haven't made any assumptions of drift or anything like that. In one sense, there seems to be some symmetry, that if the strike price is at the current price, then you're either betting on it to go up or down. And there's some gross symmetry there. Is that right? So that makes a certain level of sense. Okay? Although it's not going to be exactly symmetric there, for reasons we'll talk about in a minute. Okay? Any questions? The claim is that as the stock price becomes very, very large, okay, relative to the strike price, the value of the option tends to the strike price minus the discounted value of the, the spot price minus the strike price discounted according to the interest rate. Does this make sense? Let's think about it. Suppose, let's say, you've got an option that's payoff rate, that's strike price, and you have a call option. And the current price is here. If there's very little time, it's an enormous difference. Okay? We think that it is, in general, it is not going, there is very little risk of it falling below the payoff rate, right? Does that make sense? If so, what we would expect is that, that we're almost certainly going to execute this option. The cost of executing the option is at k e to the minus rt, okay? And the value of the option is almost certainly clear at what we have, if that's a big difference. Okay? Any questions? The same thing as a put, okay? As what is the value of the put as this current price gets extremely large? A put means you win if it falls below the strike price. Okay? Certainly if the current price is unbelievably high relative to your strike price, your put option is zero, right? You're almost certainly not going to want to sell it at that price. Okay? Any questions? So that governs that governs the put and call prices in the extremes. Any questions? Here is an interesting one. Okay? What is the put and call price? You have a fixed spot price. You know, you start out with an initial price and spot price and all that. What is the put and call price as a function of time to expiration? If these are American puts and American options, we expect that the value of them has to increase with time. Does everybody agree with that? So certainly the fact that they are, convex functions, okay, doesn't seem to be surprising, right? They're monotonically increasing functions, okay? But why is a call worth more than a put? This is actually interesting to think about. Why, if you have an identical set of set of parameters, including the time till expiration, why is it that a call option is worth more than a put? Okay? Okay, let's think about that. This is actually interesting now. Okay? The starting price is the same as the strike price. Okay, so there is some symmetry as to whether it will go up or down. There is an equal chance it's going to go down by 10%, then it's going to go up by 10%. So why would it be that the call is going to be more expensive than the put? Okay? Anybody see that? You're saying because the stock price may have a drift? That's not it. Okay? It has to do with the difference between percentage price increases and decreases and absolute price increases and decreases. Okay? Let's think about this. Suppose, let's say, that what is my profit? Let's say on a simple matter. What if I have a option with a strike price? Suppose the price of the stock doubles. If I have a call option, my price at execution is going to be 200, right? And my profit on that would be 200 minus 100. Okay, if 100 is the strike price, everybody agree that if the price doubled, I would be making $100 on my call. An equal event to a stock doubling is what? On the downside. Is it halving? Does everybody see that? So if a price halves, the price went down to 50. If I had a put to sell it at 100, what would my profit be? 50. Does everybody see that? The asymmetry here is because there are symmetric percentage movements, okay? But the put and call prices are in terms of dollar movements. You're betting that you're betting on your profits are a function of measured in dollars, not in percentages. Any questions? How many people see that? Okay, I feel there's no air in this room now, so I don't know if anybody's paying any attention. But any questions here? So that's kind of interesting. Again, as we showed before, European put prices don't always increase with expiration date, but American ones do. Okay? And that we also notice that the slope at which it is increasing here seems to taper off. Okay? Any questions? about volatility? Okay? Let's think about it, the effect of volatility on an option price. Okay? The x-axis here is the annual volatility rate. Okay? And here, suppose again we have a world where we have the current price is 100 and the strike price is 100. Suppose there was no volatility. Okay? Suppose the price didn't change. Okay? According to this, the put option value is 0. But the call option value is still something above 0. Let's think about that and to see why that might be, because that's an interesting phenomenon. If there was no volatility, what does that mean about the stock price? Okay? What's the stock price going to be 3 months from now? Exactly the same. Does everybody agree with that? Is the ability to sell something, would you pay anything? If you know that the price is going to be exactly the same, okay, 3 months from now, would you pay anything, okay, for the right to buy it at that price? Okay? And the answer should be no. Right? I mean, to sell it at that price. Now the question is, if the volatility is going to be, if you have an option to buy it in a year, okay, at a particular price, if you know it's going to stay, that the price is going to stay the same, is an option to buy it in a year worth something at that? To buy it at that price worth something? Okay? In some sense, the answer is maybe. Okay? If I own the stock now, if the price is going to be the same a year from now, what should I do? I should sell it, put the money in the bank, right? And then basically, well, I could put enough money in the bank, okay, so that the interest rate, at the natural interest rate, it will grow to the 100 to be able to buy it later on. Does everybody agree with that? So in principle, I can potentially use, okay, a call option in ways I can't use a put option. Okay? Any questions about that? Okay? So that's an argument that somehow that the effects are different, but basically the value of an option grows linearly, it looks like, as a function of the volatility. Okay? Any questions? Yes?
In that case, who will buy it? Somebody will have intended to sell it, but who will buy it?
Okay, well let's say that it is not, let's say that there is very little, okay, well let's think about it. Do we agree that I have the incentive to play this game? If I know that let's now, if there is, if there is even maybe a tiny bit of volatility, let's just go a little bit further. If I have the ability to buy it at the same price a year from now as today, there is probably no reason why I am better off not having that ability and having the money in the bank than owning the share. Okay? So I want to argue that under this condition, the option to buy it has value. Okay? And if the option has value, then someone might sell it to me. Okay, if I pay them money for it. Okay, and that sounds like I was just mumbling, so don't go what I said. Yes?
But if there are dividends here,
yes.
it will compensate maybe, or?
Factoring in then how dividends are actually, okay, that's an interesting question. That now is more complicated to think about. According to this one, the dividend rate is 0. Okay? So that's not really it. The important thing from our point of view is that there is some asymmetry here between call and put down there that is I think, reasonably, something you can sort of explain, something at the near volatility 0. In general, it increases linearly with that. Any questions? Okay. And what about interest rates? Okay, how does the value of options change on interest rates? This is kind of interesting. If the interest rate, the way to think about it is, it looks like as the interest rates increase, okay, the value of a call increases, where the value of a put decreases. Okay? Now, why is that? Let's think this thing through. In a call, I have two things. I have an option to buy it at a price, and then in order to execute it, I have to spend a certain amount of money for it. Is that right? As the interest rates go up, all other things being equal, the cost of me executing the buy later on is going to go down, right? Because if let's say there is a tremendous interest rate, I could put smaller amount of money in the bank now, so that I know that I have enough money to pay for the option, to buy the security when the option is ready to expire. So there's an argument here that somehow the cost of executing the call decreases at higher rates, so the value increases. With a put, I have the ability to sell it for $100. As interest rates get higher, the ability for me to get $100 3 months from now, okay, is less and less appealing, okay, and that is why the value of the put drops with increases in interest rates. Any questions? So think about these. They make a certain amount of sense when you think about them, and they help sort of give you a picture of what is really going on in these markets. Any questions? Okay. So that tells us that now if we have a Blackscholes equation, as we talked about before, we could, we can compute things on a calculator to price options. We can do some sensitivity analysis to figure out what the impact of these factors are. The final thing that we'd like to talk about a little bit is where does this thing come from? Okay? And the Blackscholes model is, in some sense, the model that generates it. Shouldn't be that surprising to us, because it's actually pretty similar to what we've been dealing with. Okay? It will assume, okay. So let's look at the model. The first question is that they are going to assume something about how prices are distributed. Stock prices are going to be distributed. And they make an assumption that over a short period of time, the return on a stock, which means the change in price over that time, delta S, divided by the value of the stock, the percentage up or down, that return should be normally distributed, okay, with a particular mean, okay, expected drift, and a certain standard deviation, which is a function of the volatility. If the returns are distributed according, as we'll talk about a little bit later, as the returns are normally distributed, that means the percentage up and down movements, the actual prices are log normally distributed. What does this mean? Okay? Again, there's the idea that if we have returns being normally distributed, okay, the percentage up movements and down movements, okay, there is a different value distribution for the dollar prices of these things, because the percentage increases will affect higher numbers differently than they will affect lower numbers. That's sort of the argument basically about the log normal distribution. Okay? So basically what Black and Scholes are assuming is that there is some process that is generating stock prices, okay, with returns governed by a particular mean and drift and standard deviation. Any questions? They're going to make certain technical assumptions, okay, about what kind of games you can play in an arbitrage way. They're going to say that trading is continuous. At any instant in time, you can go and make trades and rebalance your portfolio. That it is okay to do short selling. And that there is no cost for rebalancing your portfolio at every infinitesimal moment. Okay? These are, in some sense not true, but they're consistent with all the assumptions we have made, and it is hard to see how you factor in other assumptions, okay, so readily. Any questions? And finally, there are these parameters that we're dealing with. The drift, which is the expected rate of increase for the stock, the volatility, and the risk-free rate, they are all constant over the period. Okay? Some of these with other variants of the theory can be relaxed. Okay? But for now, let's assume that they're all constant. Any questions? They also assume, and this brings us back to what we talked about last class, that everything is, that there is no riskless arbitrage possibilities. Okay? There is no way that you can earn better than the risk-free rate without risk. Then this whole idea of risk-neutral valuation, okay, which is something that we've talked about last class, okay, has to still hold. It's an argument that, and so somehow this whole Blackscholes theory that we're going to talk about, okay, is based on this exact same theory that we talked about for risk-neutral valuation in binomial trees. Okay? The stock and option prices depend upon the same underlying source of uncertainty. If the stock goes up, the option goes up. Just like with what we talked about with risk-neutral valuation last time, we can build a portfolio of stock and option where somehow this source of uncertainty is eliminated. We can create a riskless portfolio from those two risky things. Okay? And the portfolio has the property that at this instance it is riskless. Because it is riskless, it must earn the risk-free rate. Okay? And that's, again, the same basic theory, the idea that we had before. Okay? Any questions? So the Blackscholes equation, just like with the risk-neutral valuation we did with binomial trees, is going to assume risk-neutral valuation. Okay? It is going to assume again that somehow that the options have to be priced at the risk-neutral rate, because if not, there would be an arbitrage opportunity. Okay? And because there is no arbitrage opportunity, we can price these things at the risk-free rate. Any questions? So all of this theory, this part should sound very similar to what we're doing. Okay? Any questions? Now, when you look at a book, what the Blackscholes equation is, okay, you end up seeing something like this. This is a partial differential equation, okay? Now, I had differential equations 25 years ago at 8 in the morning, okay? And I would not recognize a differential equation if I woke up in bed with one, to be perfectly honest with you, okay? But, so this doesn't really mean very much to me, okay? Now, if we, on the other hand, what does mean something to me is when we think about binomial trees. I understand binomial trees, okay? What you're telling me is, the theory basically is this is some kind of an equation that comes out of, okay, or implicitly when you evaluate this with the right boundary conditions, okay, this thing is going to come out to basically doing our binomial tree method, okay, with infinitesimally small points with particular values of upward and downward movements. Okay, if you think of we said that somehow, okay, this binomial tree thing used risk-neutral valuation. We talked about that last time. The only thing that we didn't really specify in a rigorous way from our binomial tree method was the value of how much was an upward move or how much was a downward move. You remember last class I gave you bounds as to what those upward and downward moves could have. Okay? But I didn't specify a particular upward or downward value. The Blackscholes formula, as we'll see in a minute, specifies a particular upward and downward value. Okay? That's going to make sense as to why they pick it. Okay? Any questions? The analogy that I want to make, okay, when we think about these things, is that the binomial theorem, okay, we talked at one point here about the binomial theorem. What is the binomial theorem? Okay, or the binomial distribution, something like this. When we got back to our world of coin flips, in the world of coin flips, the binomial distribution told us something about if we flipped n coins, what was the probability we got a certain number of heads and a certain number of tails? Okay? We could have figured that out by doing a binomial tree experiment and gotten what those probabilities were, right? The binomial theorem, in some sense, is a closed form for it. Okay? So we could think of the binomial theorem as being, so in some sense, a closed form for stock prices, not option prices, which is what the Blackscholes is for, under a discrete as opposed to a continuous model, okay, of steps. For an additive, not multiplicative, sequence of moves of one, up one, or down one at each step, versus the ones that we're going to use in specifying what the upward and downward moves assumed by Blackscholes. Okay? Any questions about it? So one argument is that if you can sort of believe that an equation pops up out of this thing, somehow I can assume that an equation pops out of this thing, if you know how to do the math. Any questions? So what are the upward and downward moves? Any questions at this point? Now is something that is not so abstract and is going to make some sense. Okay? What is the upward and downward movements that they assume in the Blackscholes model? Okay? Here they say the upward movement is 1 plus sigma, that volatility parameter, over the square root of the time parameter. The downward movement is 1 minus that. Okay? And the probability of going up or down, they have as being 1/2 plus some function of the upward rate, okay, of the expected drift, okay, mu, and the the volatility. If there is no drift, mu is 0, the probability of going up is the same as the probability of going down. Okay? Any questions here? So what is interesting about these particular values? Okay? In fact, let's write them down here. Make sure we do those. Okay. Upward movement was 1 plus sigma square root of d. Okay. The downward movement was 1 plus minus sigma delta t. And the probability, just to make sure we have it, is 1/2 plus mu delta t over 2 sigma. So what is interesting about these values? Okay? If we're going to use these values in a binomial tree model, what is the expected value up or down, okay, after one time step? Okay? We have an upward amount that we move and a downward amount that we move, right? The expected increase, okay, of what we go up is the probability of an upward move times the initial price, plus 1 minus the probability of an upward move, meaning the probability of a downward move, times the magnitude of a downward thing plus the price. If you plug in what the up and down values are, okay, what times the probability, you end up getting, I guess we can do the algebra if you want, but this is actually pretty simple, okay? The probability of an upward move, okay, is going the expected, let's say, change in time is going to be 1 plus the drift, okay, delta t over s. This sort of shows that if you assume that probability distribution and you assume that step distribution, the good thing is that after one time step, the expected amount of drift is exactly governed by this parameter mu, which is what we want it to be. Okay? Any questions here? And if you do a similar thing to compute the variance of this process, there's a formula for what the variance of something is. That's the deviation from the mean. You had that in a statistics class. If you go through and compute what the variance of it is, okay, you end up getting that the standard deviation of returns from this process is sigma square root of delta t. Which means, if you use these steps for up and down, okay, and this probability thing, what's good about it is, this is a principled way to set the Black-Scholes, the upward and downward movements, so that the amount of volatility matches what you want. This gives us a way to add volatility to our binomial tree model, okay, in a way such that the walks that we get, the prices that we get, have the desired volatility, and, okay, if we want to price stocks according to a different, a particular drift, the right mu, okay, the right drift. Any questions? So basically, these parameters give us a way to create the drift and volatility models that we want. Although, just to emphasize again, Black-Scholes uses risk-neutral valuation. So the drift that is somehow assumed in any in the Black-Scholes thing is based on the interest rate, okay, the risk-free rate, mu. Any questions? Okay, and again, when you go and do your homework here for doing your binomial tree experiments, I would say using those upward and downward steps, sizes, are probably a good idea. But you might want to experiment with other ones, okay? And if you look at the book or you do some research, there's other sort of step sizes that have certain upward and downward properties that are interesting, okay? But this one was interesting because it had the prescribed drift and volatility. Any questions about that? Any questions now about, any questions about where it comes from? This is actually a good point to sort of just assess. Okay? If we believe this thing, we now have an understanding. I now sort of see now how all the parameters in the Black-Scholes model map the things that we could do with binomial trees. Okay? And how it is that this binomial tree thing, I can believe if you carve it up to over a particular fine limit, there's an infinitesimally small thing, there will be a distribution at the end that is well defined. And at this point you need to, someone who knows enough of the mathematics, in principle, can find the closed form. Okay? And that tells me something about where the Blackscholes formula comes from. Any questions? Ultimately, this thing is going to reduce to solving a differential equation. Okay? Now, what are differential equations? Again, I had it a long time ago. I'm guessing most of you had it a long time ago. Okay, although not as long ago as me. But what is a differential equation? Okay, a differential equation is a function that is defined in terms of rates of change. That's one way to think about it, right? And a lot of financial quantities are naturally expressed as differential equations. You can see things different ways. One of the functions that we talked about that nobody got upset about in the past, because it was readily understandable, was the equation for compound interest. In fact, the compound interest can be viewed as a differential equation. Why is it? Let M sub t be the amount of money in a bank account earning compound interest at a rate R as a function of time. What is the change in wealth? Okay, if you have money growing in compound interest, what is the change in wealth between a time t and a time t plus delta t? Okay, an infinitesimally small period of time elsewhere. You're going to be earning money at a particular rate, right? You have a particular amount of money here so far, right? That's M of t. You're going to earn interest at a particular rate, okay, R amount per year, okay? Delta t is a fixed amount of time, a small amount of time. The amount of money that you're going to be earning is, instead of it being R applied for a year, it's R applied for the period of time that you have, between now and then, or delta t. So adding R times delta t, okay, gives us what the change is. The change in wealth between now and delta t from now, okay, is essentially going to be the amount of money we have times the interest rate times delta t. Okay? Any questions? Does that make some sense? In what way is that an approximation? This is not assuming over this delta t period. It's not assuming continuous compounding. Right? It says that over this period of time you're going to earn interest on the money you have. Of course, with continuous compounding, you should be earning money over here based on the interest that you had gotten. But are saying that if delta t is small enough, this is showing us what the change is. Okay? And now we want to solve the equation. dm, essentially dm over dt, is equal to R times m sub t. Okay? Any questions? When you took differential equations, you would have known that the solution to something like that was the function, basically m0, the initial condition, e to the rt. This equation solves that differential equation. Why is it? If you take the derivative of this thing, you end up getting the original expression with the interest rate dropped down. Okay? If you plug that thing in, it shows you that this equation is a derivative. It is a solution to somehow this bigger equation. Any questions about that? Okay, when you took differential equations, you recognize this. Maybe you still recognize it. Okay? But it's an example of how these things come up in financial terms. Any questions? So basically what the Blackscholes equation is, again, to show it again, is one of these differential equations. It's a partial differential equation. And the claim is the power of it. This is a very general equation. Okay? The story goes that any security, okay, whose price is dependent upon the stock price, satisfies this. That would mean call options, put options, forward contracts, things like this. Any security whose price depends upon the stock price satisfies this equation. Okay? The difference being between all the different applications has to do with what the boundary conditions are. Okay? If we get back to our binomial tree, where were the boundary conditions? What were the boundary conditions of our binomial trade? They were really over here. What was the, I guess it's maybe the initial stock price, but that was really a parameter. The boundary conditions were how much was the option worth at each of the tailing nodes. That was what the boundary conditions were. Okay? And likewise, all of these equations, the applications of these things depend upon setting those boundary conditions properly. Okay? And again, if you can set these boundary conditions as a function, okay, you can then hope to solve for the thing analytically, solve the equation analytically given those boundary conditions. That is sort of what the hope would be. Any questions about that? Okay? That's a vague sense of where this stuff comes from. Okay, and it's pretty much what I want to leave it with. Any questions? So what are the limitations of the Black-Scholes model? Okay? The good thing about it is that it is, it gives pretty good answers. And how good the answers are, you guys will have to decide, okay, when you do your homework assignment. Okay? It assumes that returns are log normally distributed. Okay? That is somehow an assumption built into the model. And that is not always true. If you think about it, right now we're going through a world where, let's say the average daily return in stock prices, we said therefore might be 1.57%, might be the mean. We are right now going through periods of time where the daily return yesterday was minus 9%. That was many standard deviations away from the mean. That was an event that is very, very rare, but clearly happens more often with real stock prices than it would if prices were distributed according to this. So one limitation to the model is that the return distribution is not bad, but not completely right. Underestimates large changes. Okay? It is a continuous model. That is a problem. Okay? Because as we notice, stock prices are not continuous. They change. The market is not always open. Okay? And stock prices do change in discrete jumps. Okay? At the very least, every stock price can't change more than a penny. By definition, the smallest change is a penny. So that part isn't true. The volatility of the stock, okay, we consider to be constant. Okay? And that is certainly not a reasonable assumption. If we look at the market volatility, certainly since I've been teaching here, the market volatility has only increased. Okay? And that is a limitation of the model. So all in all, it is, the Black-Scholes model is a good way to price options. But it is not somehow the ultimate end of options pricing. It is the ultimate end of what we're going to talk about in options pricing. Okay? But recognize that there exists a world out there where you would like to try more sophisticated models. Okay? Where some of these things can vary and some of these things can happen. All of these complications, once you do the modeling, can be neatly folded into a binomial trade. So in one sense, I'm leaving you at a point where, in principle, whatever economic understanding you can have about options pricing, you can now do and roll into your model. On the other hand, there is also the question of what analytically can you decide about more complicated models. And that is why there is a big area of options pricing theory, which we're not going to get into. Okay? But it's important to recognize why it's there. Any questions? Any questions about the Black-Scholes model, why it is a good thing, why it is a bad, why it is not the ultimate thing, and some brief sense as to where it comes from? Any questions? Okay. Any questions? Okay. So in that case, what I'd like to do is, at this point, what we're going to do next class is leave options pricing. and start to get into the issue of computing things on prices. We saw it today in class, we saw things about volatility. Volatility was a parameter computed from prices, okay? And we're going to want to start looking at how do you deal with price data, okay? What kind of things can you compute? How can you understand it in meaningful ways, okay? And that's going to be the next section of the course. Anything else? For those of you with the homework, with the project proposals, I have read the project pre-proposals. I don't want to give them back today because I didn't write the grades down, okay? And I want to make sure I get that. But for purposes of discussion, if you want to talk to me about your proposal, your projects, talk to me after class next time when I pass these things back, okay? There's two groups. There's an R group and a quantlib group. Is there a representative of the R group here? Is there a representative of the quantlib group here? Okay? I want you guys to give your presentations on November 6th. So put that on your calendar, okay, just for now. Any questions? Okay, thanks for your attention, and I'll see you guys next class. We'll start talking about price, time series analysis.